Good morning to those of you who are here this morning. You might recognize from my voice that I have a bit of a flu going on, so I don't think my voice will actually hold on for the 2 hours. So I've decided that I'm going to give today's lectures in brief outline and then direct you to the next material available on the same topics from the last year's slides. So let's do it that way. First of all, this morning we are going to talk about the analytical architecture, about how we go from the requirements, which we covered last week, to the design and UML work we have been already talking about, and how this connection between the actual architecture, taking into account the platform-specific requirements, and the first analysis of, collective requirements and domain models and such work. Also, what actually is the software architecture, what sort of things should be mentioned, or how the analytical requirements and analytical architecture transforms into the technical architecture. So, the first part of this morning, we talk about the rational unified process. Since we are collecting and defining things with the UML, it's natural that we also talk about the way of doing software with the method that actually applies or supports the UML. So the software rational unified process is a software development process. It's nothing really spectacular, considering the things like waterfall or Scrum or extreme programming or something like that. The part about the rational unified process, which is interesting from our perspective, is the fact that it actually is something that incorporates the UML design quite closely to the actually doing things approach, meaning that the best practices and that sort of stuff are also represented there, and how to use the UML diagrams and UML designs when actually doing something, meaning that this is the link between the analytical architecture and the software architecture. So, of course, process being who does, what does, when, and how, it also defines roles and milestones and development activities, but of course you should remember that the process model never should be something that imposes requirements on the organization. Organization uses the parts from the process model that they think are beneficial to their activities. So, the rational unified process actually, it's not a happy coincidence that it and UML are rather close to each other. This is because the rational unified process was defined or designed by the same people who did the UML model, and the central characteristics were more or less to enable sort of agile approaches or agile practices, the best parts of that world, into rigid and controlled process model, which would enable development of any sort of software, from the highly critical military or Medicare software to something like games and other software. So, of course, being UML, it's use case driven, and it has highly centric focus on defining how the architecture works. So, basically saying that on the design phase, we more or less have the system-specific things already nailed down, and we know that once we start the development work, we will be able to define the software. So basically, before going into the model itself more, The rational unified process actually applies most of the best practices we know about software engineering. Of course, if we have bad software development team, or we have inexperienced crew, or too little time, or too little money, we can't salvage our work. That's only natural. But the best practices, which in normal cases should enable better quality, are implemented in a rationally unified process in some ways. For example, the iterative development, meaning that we have cycles and we have milestones and internal iterations, exist in rationally unified process. We also take care of the requirements. There's actually use cases and drive to understand what the customer would need. Also things like using prototypes to collect information and constantly supervising that the requirements we want are met and that the requirements we want are actually the requirements that we should be doing. The component-based architecture is also there since the UML is there, and it's highly driven by the idea that the software consists of a number of components which are interchangeable. They are cohesive and coherent pieces of defined software which you can replace if one part is faulty or it's too slow or you just want to optimize something. Obviously, the diagrams enable us to model the software visually, and the testing work continues throughout the life cycle. When we have something that we can test, we will start doing testing work with that part. And finally, if we have to change something, we know which parts affect what parts affect what, and we also have ways to manage the work so that one group of people can work on, for example, the server end, and the other group can work on the client end when we have clear division between parts, so we can control changes to the specifications and stuff like that. So the idea is that the rationally unified process works in phases. We have inception phase, we have elaboration phase, construction phase, and transition. In these parts, the idea is more or less that the inception phase is used to capture most of the requirements. It also includes things like doing proof of concept prototypes or doing analysis on what sort of things we actually need. For example, market studies and similar activities to actually know that the software will make money, or that there's at least the probability that the software will be financially feasible. There's also design work and, of course, testing work, since we can already test the designs, for example, by ensuring that all the captured requirements are at least once tested or at least somehow represented in the design, or the captured requirements about usability are represented in the proof of concept prototype. It's important to notice that unlike other development models such as waterfall, the rationally unified process does have the same phases or activities as in waterfall. They are represented here, more or less requirements capturing, analysis, design, development, testing, quality assurance, and so on. However, the idea is that you have to do all these things, or most of these things, throughout the project. So the inception phase means more or less that the project is started and the business, logistics, and feasibility of the project is defined. The elaboration means that there's a design for a product, there's architecture, there's all the definitions needed so that it can be constructed on the third phase. Finally, on the transition, the product is launched partially or put available to customers, and the final iterations are more or less just the development of additional content and these sort of things. The workflows and these graphs here show the relative amount of work in each phase. It's important to understand that, for example, with the implementation, it already starts at inception because there might be something like testing or developing communication protocols or communication methods between server and client, or mobile phone application and the home system providing the data from, for example, server cluster, which stays with the project throughout the other phases to the final product. So you do all the implementation and testing work and design work throughout the project, but as, for example, with the design flow, it's mostly done in the elaboration and the early phases of construction, because you design most of the things before you start to do construction, and when you start to do the implementation, the need to design for future or design for the parts obviously decreases because the amount of implemented or already existing components becomes larger. Similarly, the requirements workflow stops around construction phase, because at that point we have to set down that these and these and these are the physical things or the actual attributes of the software. We can't commit to any more changes. Okay, so like I said, I'm going to skip the more detailed parts here because I have a bit of a flu and these things are explained on the course website. The one thing I want to point out from this inception phase is that, for example, the inception here builds the business model, for example, the class diagram, which explains who are working with the product and what the most important use cases are and what are the most important bits of data and these sort of things. The documentation includes the domain model and business model and all the initial list of risks, initial order of use cases, plan for elaboration phase. More or less the similar things that we have been doing with the exercises. Doing designs, having the first ideas of how the system works, what sort of environment exists for the product, and what sort of documents we have to do. For example, the business model here is, it uses a bit different notation than what the Argo UML uses, but it's more or less a use case diagram. There's passenger, there's a tour guide, and different sort of use cases. If we were doing something like a check-in system for airport, this would probably be something that the initial business model for the use cases for that particular system would look like. Similarly, additional work, there's actors or control systems and more detailed information. For example, these symbols are taken from the BCE modeling. The package and package tag here represent different pieces of information. For example, that we have to know who left and what package, and we also have to have the package tag to tell where this package is going to. And the coordinator and check-in agent are control systems here, meaning that they are the ones doing the tagging and packing and sending stuff abroad. Okay, so the domain model, like I said earlier, is also something that we already have been doing. So the elaboration phase is more or less the more detailed version of the inception. The idea is to construct the system architecture here. The system architecture being the second part of this brief summary of a lecture. The elaboration phase means that from these initial designs, gathering of the requirements and use cases, and designing the first version of architecture or the analytical architecture, which not yet have any technical parts in it, we go to something that takes into account the environment and the technical details and platform and techniques and other things which are required for practical implementation of the system. The domain model and business model are completed. We know all the risks, we have the architecture, we have all the use cases, and we have all the information about the usability. This is important because the next part is the construction phase. It's simply the heavy lifting phase, so to say, for those who are programmers. They are, this is the phase where the software is constructed. The source code is generated based on the designs, and most of the mechanical or technical testing work is done. For example, the unit testing, integration testing, systems testing, the different levels of software testing mentioned in all the pieces of literature about software testing ever. Finally, the transition is something that finalizes the product development. The final faults of the software are corrected. For example, mistranslations and stuff like that. If there are problems with the user interface, or there's problem with certain types of mobile carrier networks and these sort of things, only things that are found when actually using the system in the commercial grade environment. This is the phase where all these things are fixed. Construction phase already gives us a functioning product, the so-called beta release, which means that the software is functioning, but it hasn't been used in real life context. The transition here means that all these final activities are done, faults related to actual environments are corrected, manuals, training courses, tutorials, things like that are completed, and also all the artifacts are done. One important thing to remember with the transition is that when the transition ends, it doesn't mean that the software lifecycle ends. It only means that we go through deployment and the software stays in maintenance, and there will be further updates even after the first transition phase. So overall, the rational unified process has 4 main milestones. After the inception, there should be objectives for the product, profitability, risks, requirements. Would it be commercially feasible to produce this software? After the elaboration, we know the architecture, we know the costs, we know the implementation plan, we more or less know who we want to use for it. The construction is construction of the operational implementation, and finally the product release is something where we can start making money with the product, or we make our customer pay the fees related to that product. So finally, on the rational unified process, there's a couple of slides about it more. There's the idea that we do all these different phases in smaller iterations. So we have something like 5 cycles for inception, 5 cycles for elaboration, 5 cycles for construction, and as many cycles as needed for the transition. It means that we do the software bit by bit, adding features, adding more modules, replacing the proof of concept versions or placeholder objects with actually functioning items, or producing the first core system before first, and then doing additional parts or additional content to the software. It's more or less up to the organization what's the order of development here. So more or less usage of all the basic ideas which enable organizations to do better quality. Finally, of course, there's also things beyond software development like configuration management, environment management, or general management, all the things people, well, usually find annoying in software organizations and development work, but they are separate workflows, obviously. This is just something, the business modeling or initial gathering of requirements, analysis and design, implementation, testing, and deployment are separate from the general management. And finally, the iterations, of course, mean that on each iteration we have more or less a mini waterfall project where we do first get new requirements, additional analysis work, additional design work, implement the new features, and do testing. And when we hit the internal deadline, then everything should function as intended, and we move on to next cycle in which we do additional objectives. So basically, mostly similar ideas like with Scrum, although with the rational unified process there's more rigid control of how things happen, and Scrum only defines how the design, or more strictly how the implementation work is done. The rational unified process takes also things like the requirements gathering and analysis into account. Okay, so this was the second part of this lecture. The software architecture, of course, the idea is that what is it? It's a bunch of UML diagrams. Yes, it's definitely also that. But it's really common word. And of course we can understand with buildings that the architecture or blueprint is more or less the plan where all the plumbing work goes, or where the electric systems are installed, or what the building will look like, or how it will be constructed. But what actually is the software architecture? Of course, there's some considerations here. There's the definition that it's the method or style of building, formation or construction, and art or science of building, or the manner in which the components of a computer or computer system are organized and integrated. So, more or less, this official answer or official definition of what is software architecture leads us nowhere, because it doesn't actually tell what we have to have with the architecture. So, the architecture is a metaphor for it means that all the documentation and all the things you need to do to be able to convey your idea of what sort of software you want to build is software architecture. All the things you design, all the things you implement are that show your design about the software, or how the modules work or behave, or how the customers should be working, to show other people your design, and more importantly, allow other people to help you in the development work, or other people to cooperate with your development team. We have long since passed the era where one person could realistically define or develop everything, so we have to be able to tell other people what we are designing, or what sort of solution as a software we are proposing. It would be easy if the software development would be something like constructing things out of Lego blocks, because we know what Lego blocks look like, we know what they are capable of, so we could just draw them a picture or give them a detailed technical explanation. But since software is abstract, you can't see, or you can sort of define what sort of structure source code has, but there's no strong rules in it. So if there's 10 people solving the same problem, you will probably have 10 different solutions. Of course, you can apply something like design patterns or predefined algorithms, like with search algorithms and that sort of things. But still, if you are constructing a large system, you have to be able to show other people how things work. Also, confusingly, the architecture also has different meaning on software engineering or in computer science. Not only does the architecture refer to the entire plan of using, for example, the UML and 4+1 approach of defining things, it also means the technical architecture of systems, since there are several things we have to take into account when creating software. We have hardware architecture, network architecture, application architecture, system architecture, and finally the software architecture, which the UML and our own designs are more or less related to. Hardware architecture, network, application, operating systems, they work as they do. We have to work with those rules or understand how things should work with them, or we can create our own software. Well, we can create our own hardware, but would it be feasible to create our own computer, our own network protocols, our own operating system, or our own layer models, simply because we want to create something? So, considering a couple of words about the other architectures of software, of course the idea is that, like with building materials, we know that if we install certain sort of plumbing or wiring into our building, we can get the electricity from the municipality network, or we can get the water from the county supply, and so on and so on. So, a bit similarly here, the hardware architecture or network architecture or other things enable us to do much more with our software. This means that things like different sorts of user interfaces, terminals, operating systems, or even ways to share the components with other applications like the Common Object Request Broker architecture or CORBA are things that enable us to use existing parts or reuse existing components or use operating system libraries or modules in our software. For example, the component object model with .NET approach and in any other places, it's completely common that we use, for example, with Python programming language, some library which was written and compiled with C language, because there's design decisions which make these things compatible between each other. And for example, we can have mathematics library from C, which is really efficient, joined with the expressiveness and easiness of using Python programming language, which by itself loses performance or doesn't care that much about performance when compared to user friendliness or, well, easiness of use, whereas the C language is something that is really efficient, provided that you actually are able to do something with it. So these examples here more or less talk about the technical architecture, network architecture, and object ability to use different parts or libraries and operating system modules and so in the context of software architecture. Of course, these aren't the things you can design, but these are the things that are related to our architecture, because if we are working with external stakeholders like software systems or merging our system to some external service like the Amazon server cluster, we have to know what sort of parts or what sort of systems we can use there and design our own approach around that particular problem. Of course, these are quite low-level examples because these talk about the ability, for example, to use C# and .NET Visual Basic programming languages together, or use Python and C# and Java in the same project if we decide to use certain platform that is able by system architecture to support all these languages together. So the architecture also means how the platforms function. Of course, the idea in 70s was that we have dumb clients which we use with the server system. In the 80s, we had more things than thin clients. We had 80s and 90s, we had desktop systems, and they might send information to server side. But the idea with this talk, more or less, is that there's a huge amount of different things which technologies which affect how our system architecture should be designed, and if we are doing something which is related to anything else beyond our own project or our own product, then we have to be able to understand all the different technologies and stuff. For example, if you work with the bank or insurance company, you may run up against some software or database which has been working for almost 50 years now, because the first commercial database solutions were taken into use around 70s, and as ridiculous as it might sound, those things are still somewhere in use. So more or less what is the system architecture, or what sort of things will connect or affect my design, is actually ever increasing. Of course, if we design stuff like games or simple application, calculator for iPhone or that sort of stuff, this isn't really that relevant, because we have one platform and one programming language, couple of choices for engine and that sort of thing. But overall, the architecture, when considered from the larger perspective of including everything from the hardware to the programming languages to the operating systems, becomes quite complex. So then, why is the idea of architecture useful? Well, it manages the complexity. We can select the technologies and the solutions, and we understand what sort of things we need. If we have identified that, okay, our new software project needs to connect into a system which was written in the 80s with COBOL programming language, we might want to have one person who is able to understand that programming language, or someone who is at least capable of doing some fine adjustments to that system if needed. It also means that we can reuse existing parts, we can use services, we can use, for example, standardized interfaces, or we can reduce the amount of work required for teaching how the system works, or we don't have to create our own way of measuring, for example, how much time certain actions have taken, if we understand how the system clock functions and are able to listen into that. Also, finally, if we talk about the software quality, which is the design with the UML and doing the design work and constructing the architecture, or defining how the system should behave and what sort of components it should have before doing the implementation, we probably will have better quality simply by the virtue of having to do less revisions and changes into the system. So, going into the architecture, the idea of, starting from the 70s and, talking about the ancient Rome, before actually telling what the software architecture is why I'm talking about these sort of things. Well, let's stay here for a moment. So there's different viewpoints into what is architecture in buildings. It's the facade, it's the building structure, pipes, delivery of water and heat, electricity, and floor plan. Similarly, with software engineering or software development, it's understanding how the network works, how the hardware works, what sort of things the operating system wants, what sort of things are required, for example, to be able to use the network interface. And of course, finally, how my own software should look like. So for this, there's the 4+1 views into architecture. This means that when we are defining our software with UML, we have different views into the software, the definition of what sort of things happen with the software. We have the logical view, which includes class diagram, communication diagram, sequence diagram, state machine diagram, and object diagram. It's more or less the definition of what components will be made, how they will behave, what sort of things are they doing. So we more or less know what sort of complexity we are talking about with our components, what things they are doing, what we can take from other services, what we have to make ourselves. For example, if we have heavy mathematical calculations, we might want to start looking into something that's more close to the low-level programming languages, because they can be very efficient on doing simple things. Whereas if we don't necessarily need that, then we can select some other way to approach the problem. Besides logical view, there's the development view, component diagram, and package diagram, which is more or less about the organization of the assets during the development work. Which also means that if we want to do changes, for example, how our search engine works in our new intranet site, we know that we can take what parts we can change without having to worry that we no longer are able to use some other part of our software. For example, if we make changes into how 3D objects are rendered, it will have no effect on the activity of how the user interface is overlaid over the 3D objects or stuff like that. If we want to change the system, how user gestures are read from the touch screen, it won't affect how the user gestures are read from the gamepad, because those are two different modules, so we can just make changes to each one whenever we like. So that sort of things where the assets are and which belongs to what. Also the physical view, including the deployment diagram only, actually, tells us how the system and software and hardware are related, how the system will look like when it's installed and deployed into user, and the process view with activity diagram and timing diagram tells us more or less how the system works, how the concurrency and synchronous aspects happen in the software. Then finally, there's the +1 view into architecture, We know what parts we need. We know which parts are interconnected. We know how the system will be deployed, and we know how concurrent activities happen or what things are not related to each other by rigid timing requirements. And then finally we have the use case view, which defines how the system interacts with the world, systems around it, how users use the software. Of course, the obvious observation here is that it doesn't take into account anything about what the user interface looks like, what are the requirements, for example, that the software is fun to use, or these sort of things. Well, yes, it doesn't. That's the problem with the UML. If we want to design something for entertainment or something easy to use, we really don't have tool for that with UML. We have the technical representations, we have the technical solutions here, but for example, something like what the user interface or main screen or main view should look like isn't simply there. So that's also one additional view into the architecture and into the software, possibly with the physical view, showing what the software will physically look like when it's functioning and these sort of things, but these aren't defined on the default 4+1. Of course, it's a problem that should be fixed, but well, since I'm not the person deciding what goes into the UML3, I just have to say that it's additional thing that you should include with the documentation, even though it currently isn't required anywhere. So this is just additional list of how the what sort of things the 4+1 view includes. Also, the thing to point out here is that there's a bit of a mix-up with the terminology. Some people talk about the development view and some people talk about the implementation view. Some people say that the deployment view is actually physical view because the only thing currently in the physical view is the deployment diagram. So, but that actually only adds into the confusion because the deployment diagram depicts how the system physically looks like. The hardware cabling, the protocols between different places where the software exists, other physical structures. Also, if I would make the decision on usability aspects or user interface design or that sort of things, I would put them there because they are more or less physical thing what the user sees when they use the software. So couple of things to say about the how the UML is used. For example, this is the package view. This more or less shows the dependencies between the subsystems. Like I said with the example, for example, we can decide that we have the core system, the 3D rendering system, the user interface overlay, and different methods of inputting information in different subsystems so that we can define them into their own areas or own domains. For example, in this application, if we want to do something about which is in services, we know that we will not have problem with the presentation. There's some things in application which calls services, so we just have to take into account the interface between the application and the service module. We don't have to care about anything else. The service module doesn't use anything from the main, it doesn't use anything from the persistence, and also doesn't use anything from the presentation. Of course, if you use some more advanced UML development software, this is also what creates your indexing for your documentation. Since if we are using rigid UML, we might end up with the huge amount of diagrams, hundreds of diagrams, if including all the different versions of the diagrams. So this also gives us more or less the way to create indexing. For example, I want to take everything that's on the domain model there. I just open or use things in that package and know that all the relevant information is there, and the system shouldn't be showing me anything up from services or presentation. So that's also one thing. Additionally, the layer thinking here, we go from the certain high-level areas about the applications and what the business-specific activities, what areas of business use what applications, what middleware are these business-specific layers or functions using, and finally, this middleware like window management system or database management, are they using external server side or are they functioning with our own operating system? So more or less using the package diagram to define different ways of dividing the information. Finally, some free-form picture, which actually is also one of the most common ways of defining the architecture. The component diagram here, for example, defines a couple of objectives, one executable from the local system, and a couple of libraries which are all somehow interconnected. We might as well use any information and we define what is dependent on what. And for example, in this example, we have web pages, we have executable software defined and libraries related to that software. The deployment diagram, which here is shown with the UML1 notation, is also one way of defining things, but well, it's more or less about the physical representation. We have desktop system, we have a registration server, we have a billing system, which is a legacy system. We didn't build that, we just use that system from existing functions. We have external desktop PC, which is connected over public access network, and finally we have the course catalog system. This is from the example about the course management middleware, which was example on the earlier iteration of this course. So more or less the deployment diagram shows the different systems and where the different services like server-side applications, the actual database or user interface and these sort of things exist. Of course, considering something like the cloud services or modern technology in general, the deployment becomes a bit vague, because even though we are using the software from the user mobile phone, we might have the actual application stored in some cloud from which the system is downloaded to the handheld system or front-ended in the handheld system only for the period of the usage, and finally the data may be stored somewhere else besides that certain cloud which is distributing the executable software. So there's, of course, things aren't this clear cut, but the idea is more or less there. Finally, there's some additional things in the UML2, like the composite structure diagram, which enables us to define more detailed information about our system, and component diagram, which from the this component diagram, which is more or less UML1 mishmashed with free-form pictures, is now actually defined in more detail. Finally, the deployment diagram of this example shows this new notation. The boxes are still there, but the services and applications, for example, web browser and the web interface for the server, databases, and these MySQL database parts are more coherently and displayed in more detail. So, finally, what should I define for my system architecture, software architecture? So this is, for example, what the rational unified process has. It has several things here. The architectural representation, use case view, logical view, process view, deployment, implementation. Also things about the size and performance, data, what sort of data we are handling, quality, which are the quality metrics we want to use, and also things like what sort of goals and constraints we have, additional requirements imposed by the software platform or system platform, for example, in that number 3, and also if we want to add things like user interface and stuff like that, we can put them, for example, into the deployment, or like I have said earlier, that since we aren't slaves of the rationally unified process documentation or any process model really, if we have to define what the user interface looks like, or we want to do that, we can just add it as a chapter 12 or additional part on everywhere we like. If we need to have the user interface defined, then we take one template and add it there. But this is the example of how rationally unified process does the software architecture documentation. So, overall, the architecture in software or software development is fuzzy thing. It may be the hardware, it may be the network, it may be the software we are building, but anyway, it enables us to exchange information and design stuff before we try to implement things. The idea of architecture is to describe or define the non-functional requirements, manage the complexity of doing development work, division of work, meaning that what sort of people we need, how many people we need, when we are doing different things, disseminating knowledge and information, meaning that everyone can see, more or less see or read other people's intentions and ideas of what we want to do, and it also enables us to make decisions about technology. If we want to have performance, we need to pick that certain, we might want to pick certain platforms or certain hardware. If we want to have system that's easily approachable by new developers, we don't have experienced crew, we might want to use some existing services. If we have, for example, Windows platform, we might want to use .NET development platform, or if we are making mobile game and we want to reach the Android and Apple iPhone markets, we have to use these sort of engines and these platforms so that we can actually release stuff for those platforms. If someone from Microsoft wants to buy us the application for Windows Phone, they then have to buy or pay enough for us to redo the project with that hardware platform. So overall, architecture is useful for defining things, and like I said on the start, everything you do to define things about how the system should behave, look, function, or any thing you design for your work is part of the software architecture. Anyway, on final note, I also have to decided to announce it here this morning that next week we will not have this lecture. I am on staff training, I would have to have only 30 minutes to talk before I have to go there. So we might as well cancel next week's lecture, and I will provide you with an online replacement for next week's topics. Before I decide what to record and what to do, the next week's topics are handled by the video 72, 81, 91, and 92 from the online archive. So next time I will be giving you a lecture. It will be a Tuesday 28th of this month on the first demo lecture of this course given on Tuesday in classroom 6325 on 2 p.m. On afternoon. So next week we will have the final exercises of this period. Then the next thing is the deadline of project 1, and then we will start with the demo lectures and project 2 in 2 weeks. About the replacement things for this morning, if you want to find more detailed information about the rationally unified process, there's things in the video archive, as there are more detailed information about the 4+1 views, or what is software architecture and what is system architecture. And there's also actually separate lecture on software architecture on the lecture recording archive from last year's course. The details might vary a bit, but the information or stuff about the software architecture is the same. Of course, ignore the course-related information that's from the last year's implementation. Okay, good. Let's end here.